Hello, my name is Petros Papadopoulos. I am a first-year PhD student at the Department of Industrial and Systems Engineering at Rutgers University, and I am very happy to present in this poster session of MAP 2020 our research group's work on opportunistic maintenance for offshore wind farms. In this work conducted by me, Professor David Coit, and Professor Ahmed Azizazad from Rutgers ISE, we focus on maintenance scheduling problem for offshore wind turbines by formulating an MIP which employs an opportunistic strategy to minimize total plant costs. The use of the word opportunistic in the context of this work results naturally from the fact that performing maintenance tasks and generally any operation in offshore settings requires the exploitation of opportunities created by the meteorological conditions at the location of the site. And as we are about to discuss, this strategy is very important for making those operations more efficient, minimizing the total cost of the maintenance plan and subsequently reducing the total cost of offshore wind power. Why do we target O&M specifically? Now, at the moment, wind power makes up about 7.3% of the total energy mix in the US, and this percentage is estimated to increase by almost 500% by 2050, covering 35% of the future demand in power. And while offshore wind power is still in its infancy in the US, there are many ambitious expansion plans over the next few years. Now, operations and maintenance in offshore wind farms currently account for about 30% of the total project cost. And these figures are so large because of the many challenges that arise in offshore settings. And the most important of them are, first of all, the limited site accessibility. So offshore wind farms are often installed dozens of miles off the shore to take advantage of the stronger winds. So frequent maintenance visits are not always an option, and that always usually leads to more frequent failures. Now, the second highest contributor are also the high production losses. And this happens since offshore wind turbines usually have much greater capacity that can currently reach 10 megawatts and are estimated to reach 15 megawatts in the next few years. So when they are shut down during maintenance or when they fail unexpectedly, the revenue loss is tremendous. And finally, they are the safety considerations due to harsh weather conditions, which many times do not allow for scheduled maintenance to go as planned. So, what is the usual practice and what do we propose in this work? Now, the industrial practice of O&M planning is usually either time-based or reactive, meaning that preventive maintenances are either pre-scheduled by the turbine manufacturer or a condition monitoring system, or they are unplanned and occur only after the turbine has failed. And although many research studies have been conducted to minimize the total operational costs of wind, most of them do not consider the offshore-specific setting. And of those that do, to the best of our knowledge, none is considering all the three major contributors of O&M costs. Now, our focus is to make a holistic model which uses an opportunistic strategy and considers all those contributors all together by, first of all, grouping maintenance tasks whenever possible, while scheduling maintenances during low wind periods, and at the same time considering site accessibility and safety considerations for the crew workers. Now, as we mentioned earlier, the model we constructed is a mixed integer linear program whose objective is to maximize the total profit that is realized by the wind farm operator during a specified period of maintenance. Now, to do that, we separate the time framework into two independent horizons. The first is the short-term horizon, which considers discrete hourly intervals for the day ahead. And the second is the long-term horizon that is discretized into daily intervals, starting from the day after the next until the end of the maintenance period. Now, the realized profits for each time horizon are calculated independently, and they are combined into a single objective function, which is maximized. Now, to give you an idea of what each profit term is comprised of, we present the following equations. The two equations are very similar. Their main components of both equations are, first of all, the revenue from power sold at price pi, then the maintenance costs, which are either preventive or corrective, crew hourly payment, and vessel rental, and they are all multiplied by their corresponding cost coefficients. And also note that in the short-term horizon, we also use overtime for crew workers. Now, other constraints in the model also include crew access, turbine availability and power output, and maintenance actions, and also residual life estimates. Now, to illustrate how the model works and what it uses as inputs and outputs, let's consider a case study of a small offshore wind farm comprised of 10 5-megawatt wind turbines that requires some maintenance tasks to be performed over the period of 15 days. Now, let's assume that we obtained the residual life estimates for each of these wind turbines, which we will treat as deterministic preventive maintenance deadlines in the context of this study. Now, what this means is, for example, if for some reason we miss this maintenance deadline, the turbine will fail and will need corrective maintenance to be brought back online, which in general is more expensive than preventive maintenance. Now, to simulate the meteorological conditions we obtained wind speed and wave height data from NYSERDA's floating buoy, which is deployed in New York Bight, in proximity to future offshore wind farm sites. Now, to get the power output profile for the wind turbines of our case study, we use power data given as a fraction of nominal capacity of a turbine from an operational onshore wind farm. Now we use the binning method to calculate the corresponding power output for the wind speed data that we obtained from NYSERDA's buoy. Now, given the wind speed and wave height profile over the optimization period, we also consider the period when it is safe to perform a maintenance. And assuming that the maintenance task we must perform requires a medium-sized crew transport vessel and access to the turbine's nacelle, access restrictions apply when the wave height is greater than 1.5 meters and when the wind speed is greater than 15 meters per second. Now, in the figure, you can also see that when either the average wind speed on the left y-axis or the average average wave height on the right y-axis surpass the respective safety limits, access is restricted. And we denote that by setting the background color as red or green when access is restricted or not, respectively. And this is the result of the optimization. In the diagram at the top, we can see that the average power output for all the wind turbines in every hour. And in the diagram below, you can see the scheduling plan, which can be interpreted as a Gantt chart with one task for each machine. Note that for the case study, we also assume that we have 2 maintenance crews available, so no more than 2 tasks can take place at the same time. Now, from the scheduling chart, we can see that wind turbines 1 and 2 require corrective maintenance, and since maintenances could not be scheduled before their deadlines, while the rest are preventive. We can also observe that maintenance tasks were grouped aggressively to avoid unnecessary vessel dispatch costs, and at the same time were scheduled during periods of low power output to avoid high revenue loss. Now let's see the summary of the results. For the results part, before we see the cost performance, I would like to focus on the computation time and optimality of the model. Now, the model was solved in a standard laptop using IBM CPLEX and GAMS. The interesting part is that the average computation time for an optimal solution is much less than 30 seconds, and we used an optimality gap criterion of 0.1%. And this is the result of the separation of the time framework into 2 separate horizons, which greatly reduced the total number of variables in the optimization. Now, to see the cost effectiveness of our strategy, we compared it to a non-opportunistic strategy where we consider no accessibility and no vessel dispatch cost. The time-based strategy, where the deviation from the pre-specified schedule is penalized. And finally, the reactive strategy, where we assume that we have no knowledge about the time that the turbine will fail, and we only perform corrective maintenance. Now, we use 80 different weather profiles and obtain the corresponding plan costs for each strategy. Now, in this bar chart, we see the % increase of plan costs for the 3 strategies that we mentioned earlier, compared to the solutions of our opportunistic model. We can immediately see that our model always produces the least cost solution, while the non-opportunistic strategy is on average 20% more expensive, and the time-based and reactive strategies are 50 and 200% more expensive respectively. Now, for the summary of the conclusions is that from this comparison we saw that our model always yields the best results, and so it is efficient cost-wise and also computation-wise. And we also highlighted through this study the importance of employing this opportunistic strategy in offshore wind farm. For a full list of references, please contact me through my email. Thank you.